Okay, sir.
All right. So in this session, we'll be looking at electric dipole and the numericals from this section, from this particular topic. Okay. So to start with, what is an electric dipole? What is meant by the term dipole? Di means two. So obviously there are two poles for this system. Okay. So a dipole is nothing but a system of two equal and opposite charges. See this minus q here and plus q at a distance of say 2a apart, right? 2a is a small distance actually. All right. So we have a system of two equal and opposite charges separated by a distance 2a. This is known as a dipole. All right. So the dipole has what? Dipole has a minus q and a plus q as well. Charges are equal. Look at this. This is q. This is q. The charges are opposite. One is negative. The other one is positive. And look at the distance between the charges. This is taken as 2a. Right. Or, you would better take it as 2l. Okay. Because in some cases, you will need half the length of the dipole. So the problem is, if I take the length as L, half length will be L by 2. And the equations may look cluttered. Instead, I use the letter 2, I use 2L for the length of the dipole. So that half the length will be what? L. Okay. So what is a dipole? A dipole is a system of two equal and opposite charges separated by a very small distance. See, this distance is ideally 0. 2L is very, very, very small. It's infinitesimally small. This distance is very small distance. And like I told you, I have to take it as 2L because in some cases, I'll need half the length of the dipole. Okay, right. That is point number 1. So we have seen what a dipole is. Now, what is dipole moment? Dipole moment is defined as the product of one of the charges and distance between the charges. So dipole moment is what? The product of one of the charges, either of them. The magnitude has to be taken. You can take either minus q or plus q. But anyway, you are looking at the magnitude only and the length of the dipole. As you can see, this is a vector quantity because 2L is a vector quantity. And conventionally, the direction of dipole moment is taken from negative charge to positive charge. Negative charge to positive charge. Don't ask me why. That is by convention. Across the world, by convention, we take the direction of dipole moment as from negative to positive. So dipole moment direction is from where to where? Negative charge to positive charge. That is by convention. And the third point is, what is the unit of dipole moment? Unit of dipole moment, charge's unit is coulomb, distance is measured in meter, so the unit is coulometer, or sometimes in chemistry you use dBi for the unit of dipole moment, dBi for the unit. Anyway, in physics we don't use this quite often. Instead, we have coulometer as the unit of dipole moment. And then the fourth point, what is the equation for electric field intensity due to a dipole? See, I have 2 points here. One point is on the axis. This is an axial point. Axial point. No, where is that axial point? At a distance of, I draw it here, okay? I draw it here much closer. At a distance of r from the center. So where is the point considered? The point P is at a distance of r from the center of the dipole. And this is called an axial point. Why is it called axial point? It is on the axis. At that point, if you want to find the electric field intensity, the equation is what? E axial is given by 1 by 4 pi epsilon 0 into 2p over 2p divided by r cube. This is a simplified version, 2p by r cube. While doing the derivation, this is one of those two derivations you have in this section. There are two derivations which I'll do in the end. But for the moment, you just have to see the equation 1 by 4 pi epsilon 0 into 2p by r cube. But till date, they have never asked questions based on these equations. This is axial point. Then there is one more point called equatorial point. What is equatorial point? You draw a bisector to this, perpendicular bisector. Look at that. It is perpendicular bisector. It is perpendicular. At the same time, it is bisecting the dipole. Bisecting means what? Bisecting means dividing into two, bisector, perpendicular bisector. And at this point, which is again at a distance of r, The electric field is given by the half of this, 1 by 4 pi epsilon 0 into P over R cube. So these are the equations. This is the first set of equations you have, and I'll come back and do a few more things. I'll tell you, did you understand this? I'm asking. What is a dipole? An electric dipole is a system of two equal and opposite charges. Look at this, plus Q and minus Q and plus Q. They are separated by a very small distance. The very small distance is usually taken as 2L for mathematical convenience. All right. And half length is L, half length is L. All right. And dipole moment is a quantity that tells you something about the dipole. Dipole moment. Never ever forget this. It is the product of one of the charges and distance between the charges, Q into 2L. Okay, and its direction is from where to where? Negative charge to positive charge. That is by convention. Across the world, you're taking the direction from negative to positive. And then the unit is what? Charge unit is Coulomb, distance unit is meter. So that would make it Coulomb meter. Coulomb meter is the unit of dipole moment. And then we had axial field and equatorial field. Axial field means what? On the axis at a distance of r, what is the electric field strength? I haven't told you about electric field strength yet, but anyway, you have seen this in school, so you have an idea, right? Electric field strength due to a dipole. At an axial point is 1 by 4 pi epsilon 0, 2p over r cube. And at an equatorial point, 1 by 4 pi epsilon 0 into p over r cube. And then, you know, we have a couple of more things here. Then we'll go to the question paper, okay? Right. So we have a system here. This is a dipole. I'm going to keep a dipole in a uniform field. This is a uniform field. Okay. Uniform field means what? All the lines are parallel, as you can see. All the lines are parallel. This is called a uniform field. While this is a non-uniform field, as you can see. Non-uniform field. Why? The field lines are not parallel, right? So this is non-uniform field. The field value is different at different locations. But here the field lines are parallel. They are equally spaced as well, which means it is a uniform field. Am I correct? And if I keep a dipole in here, look at this, a dipole here. This is a plus Q charge and this is a minus Q charge. In which direction is the dipole moving? You know, this is a field line. Field line is from where to where? Field line is always from positive to negative, positive to negative, positive to negative, positive to negative, again positive to negative. The lines are towards the right. That clearly tells you that there is a plate situated over here, another invisible plate situated over here, right? So anyway, the positive is on the left side, negative is on the right side. How do we know? Lines are expected to go from where to where? The lines are supposed to be going from positive to negative, positive to negative, positive to negative. All the lines have been drawn. Then I have kept a dipole here. What will happen to the dipole? This plus will repel this plus to the right. So it has a force QE, electrostatic force. This plus will attract this minus towards it with the force QE. So the dipole has how many forces? Two forces QE each. So what will be the net force on this? I can say that the net force is equal to 0. Very, very, very important question. Many times asked in foreign papers, CBSE examinations, okay? What is the net force on this dipole? The force on the dipole to the right is QE. The force on the dipole to the left is QE. They are equal and opposite. You put it on the center of mass. You put this on the center of mass. They are equal and opposite. They will cancel each other. Net force is equal to 0. But what about torque? There is a torque acting on it. Why? Because look at this. This is my dipole. If I pull this side to the right and if I pull this side to the left, you know, the system will rotate, right? See, just imagine I'm holding the dipole like this. I'm pulling it from this side. I'm pushing it from this side. What will happen to the dipole? The dipole will rotate about center of mass. So the dipole has a torque. Whose derivation you have done in school classes? It is P E sine theta, or vector tau is equal to vector P cross vector E. Why have I written so? Because this one looks like A, B sine theta. A, B sine theta is what? A cross B. So P E sine theta is what? P cross E. Okay, so I'm sure that force is equal to 0, but torque is not equal to 0. Torque is not equal to 0. How about this side? I'm keeping a dipole here. Look at this. Again, a dipole. This has a force of QE, while this has a force of QE dash. Why have I written different forces there? Because it is a non-uniform field. This is a uniform field, uniform electric field, and this one is a non-uniform electric field, okay? Non-uniform electric field. What will happen here? The dipole has a torque. Already dipole has a torque because both the ends are being turned, given forces, right? So the dipole will rotate. At the same time, the dipole will have a force also. Force is not equal to 0. Why? Because one force is QE dash, the other force is QE. Will they cancel? No. Here the forces cancel because the force to the right was QE, the force to the left was QE. They being equal could cancel each other. QE and QE are cancelling each other. So the net force is equal to 0. But even then torque is there. The dipole will rotate, only rotation. But here what's happening? One force is QE, the other force is QE dash. So the dipole is rotating. At the same time, the dipole is moving in a straight line as well. Why? Because dipole has a force also. The forces has not been cancelled with each other. The forces have not been cancelled with each other. Understood? Torque is already there. Torque not equal to 0, torque not equal to 0. Force not equal to 0, force equal to 0. And this question, trust me, it's a very, 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 very important question. They'll ask like, a dipole placed in a uniform field experiences no force. Explain why. Or a dipole placed in a non-uniform field experiences both torque and both force. Why? Did you understand this? Section A, based on electric dipole. Question number 1. A dipole of charges plus 2 microcoulomb and minus 2 microcoulomb and length 5 centimeter is kept in an electric field of strength 2 into 10 power 7 Newton per coulomb. Calculate the torque and net force on the dipole. It's a repeated question. Okay. So a dipole of charges plus 2 microcoulomb and minus 2 microcoulomb. So let us write whatever is given. So charge is given 2 microcoulomb. Micro means what? 10 power minus 6. So charge is given. Q is equal to 2 microcoulomb. 2 into 10 power minus 6. And then length of the dipole is given. And be very careful while writing. Length of the dipole should be taken not as L but as 2L. 2L is given as what? Length of the dipole is given as 5 centimeters. So 5 into 10 power minus 2 meters. Centimeter is to be converted to meters. And then in an electric field of strength, 2 into 10 power 7. Electric field is given 2 into 10 power 7 Newton per coulomb. You've been asked to find what? The torque and net force. So let us write one by one. This is a basic question, easy question. Torque is given by what? I told you torque is given by P into E. Torque is given by P times C. All right. So P times, usually it is P is sine theta, but don't worry about theta. Theta is not mentioned, but they are meaning what? They mean to say if not given, you can take theta as 90. They are talking about maximum torque. Maximum torque. That means theta is sine 90 there. Anyway, let us put this. What is Q? What is P? Q into 2L into electric field. So let us put them over here. What is Q? 2 into 10 power minus 6 into 2L is there. 5 into 10 power minus 2 into electric field is there. 2 into 10 power 7. So let us multiply 2 into 5, 10. 10 multiplied by 2, 20 into 10 power minus 6, 10 power minus 2, 10 power minus 8. 10 power minus 8, 10 power 7, 10 power minus 1. So one place down it is 2 Newton meter. Newton meter is the unit of torque. And they are asking you to find the net force also. Net force is what? Net force is easy to find out. QE plus minus QE. I told you that it is a uniform field. Why is it uniform field? Because field value is given. If it is given, that means it is uniform field. But don't worry, they won't ask you to find the force in a non-uniform field. Okay. If they ask you to find the force, it's going to be in a uniform field. I'm repeating one more time. What is the question? You've been asked to find the torque. So what is the equation for torque? We will learn torque equation is actually P sine theta. You may have a confusion there. Theta is not given. How do we proceed then? If theta is not given, they mean to ask you what? Maximum torque. Maximum torque means sine 90 should be used. Sine 90 is 1. So I can simply write P. Torque is equal to P. So P is what? This P value we have done, it is Q into 2L. into E. Q is what? 2 into 10 power minus 6. Then 2L is what? Length of the dipole 5 into 10 power minus 2. Then E is 2 into 10 power 7. You multiply and find out, you get 2 Newton meter. And then they ask what the force is. The net force is what? It is obviously placed in a uniform field. So the force to the right is QE. Force to the left is QE. They are cancelling each other. Did you understand? Question number 2. Charges minus 2Q, plus Q and plus Q are placed at locations 0, 0, 0, A and A, 0 respectively. So where are the charges placed? Charges minus 2Q plus Q and plus Q are placed at locations 0, 0, 0, A and A, 0 respectively. So let us draw the figure first. I am drawing the X and Y axis coordinate system. I am going to place the charges. Where are the charges placed? Look at the sequence. Minus 2Q is placed where? 0, 0. So I have a minus 2Q placed here. Minus 2Q at 0, 0. Then where? Minus 2Q is placed where? Minus 2Q. I have a minus 2Q placed at 0, 0. Then what? Plus Q and plus Q are placed at 0, A and A, 0. 0, A means what? 0, A means right here. A, 0 means here. This is A, 0. This is 0, A. Right. I have the locations. What are the charges placed? What are the charges placed? This charge is plus Q. This charge is plus Q. Right. It's a typical question. Okay. Find the net dipole moment of the system. Also illustrate the direction of resultant dipole moment. Read the question again. Charges minus 2Q plus Q and plus Q are placed at locations 0, 0 minus 2Q, A, 0 plus Q, A, 0, A plus Q. You have to find what? The net dipole moment of the system. And when you look at the system, you may be confused. Why? Because I said in the beginning that a dipole consists of only 2 charges. But when you see here, there are 3 charges. So how can you resolve this? I'll tell you. I'll draw an equivalent diagram now. I draw the system, coordinate system again. I'm going to make it a dipole. How do I make it a dipole? I'll split this minus 2Q into 2 charges. 1 minus Q here, minus Q, 1 minus Q here. Both are at the origin, actually. Both are at the origin. I'm drawing them very close to origin, very close to the origin, okay? So I have just split what? This minus 2Q at the origin into 2 parts, minus Q, minus Q. Then what? I have a plus Q here, plus Q here. I have a plus Q here. At which all locations? Which all locations? This location is what? A, 0. This location is what? 0, A. Now I got 2 dipoles. Look at this, one dipole here, minus Q plus Q. I have one dipole here, minus Q plus Q. Okay, I can find the resultant. How do you find the resultant? I'll tell you how to find the resultant. What have I done here? I have just split this minus 2Q into 2 pieces. Minus Q, minus Q. Both are at the origin, still at the origin. Okay, but in order to differentiate them, I have just drawn them slightly apart. What? You know, I got 2 dipoles now. Where are the dipoles? I am drawing the dipoles from negative to positive. This is my first dipole. Okay, negative to positive, first dipole. Where is my second dipole? Negative to positive. Look at that, look at that. Negative to positive. I have second dipole. Right. How do I find the resultant? If I want to find the resultant, I must complete the parallelogram. I must complete the parallelogram. I must draw the diagonal. That is how I find the resultant of 2 vectors. If I want to find the resultant of 2 vectors, see this? I'm taking the resultant. That is how I take the resultant. So how do you find P net? This is my P net. Okay, I can find P net here. Tell me what P net is given by root of, 2 vectors are to be taken resultant. Tell me what? First vector square plus second vector square plus 2 into P into cos 90. Why do I take this? Do you remember parallelogram law of vector addition? This is how you take the resultant of 2 vectors. P square plus Q square plus 2PQ cos theta. You have done this a million times in class 11. So hope you remember this. That is how you take the resultant of 2 dipole moments. This dipole moment is P. This dipole moment is also P. They are identical. How do we know if they are identical? Because minus Q plus Q, minus Q plus Q. Location is A, location is A. So identical dipoles, right? Same charges, minus q plus q, minus q plus q. Same length A, same length A. So I can find the resultant using this. Why do I take 90? Look at the angle between them, 90, cos 90. So cos 90 part will vanish. What do we have then? Root of p square plus p square, root 2p square. That is equal to root 2 into p. I take the square root. That is equal to root 2 into, what is p? Dipole moment. What is dipole moment? One of the charges into distance between the charges. Distance between the charges is what? Distance between the charges is what? A. Look at the distance there. So this will be the final answer. They have even asked you to mark the direction of resultant dipole moment. This is the direction of resultant dipole moment, vector p net. Did you understand? Read question number 3. Two small identical electrical dipoles, AB and CD, each of dipole moment P. Two identical electric dipoles, AB and CD, each of dipole moment P are kept at an angle of 120 as shown. So there are two dipoles kept at 120. Let us draw the figure. Draw the figure. Let us draw this together now. So this is X and Y. First dipole is here. This is plus Q and this is minus Q. Okay, plus Q and minus Q. And then what? Second dipole is here. Second dipole is kept here at this angle. This is minus Q and this is plus Q. And they are making an angle of what? They are making an angle of 120. They say that they are making an angle of 120. Okay, I've just redrawn the figure given. No, figure is given in the question. Two small identical electrical dipoles. Identical, remember, they are identical. Minus Q plus Q, minus Q plus Q. Same length as well. Okay, so these are identical dipoles. Kept at what angle? Kept at 120. And then what is the question? What is the resultant dipole moment of the combination? What is the resultant dipole moment of the combination? If the system is subjected to electric field E, directed along positive x direction, what will be the magnitude and direction of torque acting on this? Okay, read it again. Second part we'll do later. Okay, we'll do part by part. What is the resultant dipole moment of the combination? So first thing to find out is the resultant dipole moment of the combination. Okay, that we'll do first. Second part is, if this is subjected to an electric field along x-axis, what will be the torque on it? Right. What is the magnitude and direction of torque acting on it? I'll tell you. First of all, I have to find the direction of this. I'll draw x and y here. Here the problem is, I have a dipole here. No, where is the dipole moment starting? Negative, right? So I have this dipole moment here. This is dipole moment. The tail of the pen is where? At negative. And the head of the pen is where? At positive. In such cases, what you should do is, you should push it little down like this, so that the tail is at the origin. Tail is at the origin. So I'm drawing it here, okay? So I'm just drawing it here. This is my dipole. This is plus Q. This is minus Q, minus Q. So where is the tail? At the origin. Look at this. I've just done what? I just pushed it little downwards like this, like this, like this, like this, like this, like this, so that the tail is coinciding with the origin. Similar way, I have to push this dipole up. Why should I push it up? Like this, like this, like this, like this, so that the negative goes to the origin. Understood? So I have my second dipole here between this point and this point. Okay, this point and this point. This is my plus Q. This is my minus Q. I have two dipoles now. What are the dipoles? Look at this. One dipole in this direction, another dipole in this direction. What is the angle between them? The angle is 120. They have given, no? The angle between the dipoles is 120. Look at this. I'll show. Look at the black pen and blue pen, okay? This is black pen, this is blue pen. They are crossing like this in the middle. And I'm pushing this down like this, like this. This is pushed up. So look at this. Now what do they make? They make an angle of 120. Look at that. I've taken an angle 120 there. Understood? How do you find the resultant of them? Complete the parallelogram. Look at that. Look at that. Complete the parallelogram. Complete the parallelogram. This is how I complete the parallelogram. I can complete the parallelogram. See this? Complete the parallelogram. Complete the parallelogram. I just draw the completion here, no? Complete the parallelogram. Draw the diagonal. Look at this. Complete the parallelogram, draw the diagonal. This is one vector, I can call it P. This is another vector, I can call it P. They are identical, no? In every sense, right? Every sense, right? And I have to find the resultant of those two. How do you find the resultant? P net is given by root of first vector square, P square, like in the previous question, plus second vector square, P square, plus 2 into P into P into cos 120, because the angle is 120. Tell me what? So that is equal to root of P square plus P square to P square plus 2P into P to P square. Cos 120, if you don't know, I'll tell you, minus 1 by 2. So this 2 and 2 are cut. You get what? Root of 2P square minus of P square, P square. What do we get then? Root to P square. So the answer is P. So resultant dipole moment is how much? It is P. So this is my P net. It is equal to P. And it is in which direction? It is making what angle? Look at the angle there. This angle is 120. This angle is 120, no? And this line is bisecting it, right? Why bisecting? Because this vector and this vector are identical. This one and this one are identical. Which means if you draw the resultant, that will be bisecting. So this angle, this much is how much? 60. Because the total is 120. If that is 60, what is this angle? 30. So it is making what with x-axis? 30 degree with x-axis. I'm repeating this one more time, then I'll ask you, okay? So what is the question? We have a system of dipoles. See this? First dipole. Look at the first dipole. The tail is always negative. So keep in mind, tail is always negative, head is positive. Tail is negative, head is positive. So I got two dipoles like this. Okay, they are intersecting in the middle, and then what? I'm pushing this up, and this is pushed down, so that the tails are coinciding. Now this is how the system would look like now. Look at this, I have just drawn it here. And then what? I have identical dipoles here. I have to find what? The resultant of them. Tell me what? I have to complete the parallelogram. I have to draw the diagonal. And diagonal will give me resultant dipole moment. What is resultant dipole moment? P square plus 2pp cos 120. Why cos 120? Look at the angle there. It is 120 given in the figure, 120. Dipoles are making 120 with each other. So tell me what? If that is 120, half of it is 60. Why? Because I said this vector and this vector are identical, no? If vectors are identical, the resultant will bisect the angle. So total angle is 120. This will be 60. Since this is 90, if this is 60, this has to be what? 30. So angle is 30. Did you understand this? Okay, so we have done the first part. We got net dipole moment as what? Net dipole moment is P itself. This was P, the resultant is also P. Second question is, you are subjecting the system to an electric field. Electric field is in which direction? X direction. Electric field is in X direction, they say. Read the question again. If the system is, second part, read it again. If the system is subjected to electric field E directed along positive X direction. Okay, so electric field is directed along positive X direction. Then what will be the magnitude and direction of torque? What is the equation for torque? Torque is given by P sine theta. So I can write, what is P? Torque is given by P sine theta. What is P? P is P itself. What is E? E is E itself. Sine theta is what? Theta, I would say it is 30. Why? Because electric field is to the right on the x-axis and dipole moment is in this direction. They are making what angle? 30 degree. Electric field is on x-axis. Electric field is here along x direction and dipole moment is here. They have an angle of 30 in between. So I have to put that value, sine 30. That is what? P into E into sine 30 is 1 by 2. So the answer is P by 2. Did you understand? Okay, so what is the second question? You have to find the torque. Torque is given by P E sine theta. Okay, that is P into E into sine of angle is what? Angle is between P and E. What is angle between P and E? Where is P? P is in this direction. Okay, where is E? E is on x-axis, they say, x-axis. I can draw it wherever I want, x-axis, no? So they are making what angle? 30 degree. P is in this direction, electric field is on x-axis, the angle is 30 degree. Sine 30. Sine 30 is 1 by 2, that is P by 2. They are asking you to find the direction also. Where is the direction? You know, you go back to class 11 physics, where you learn the direction of cross product. The direction of cross product. Where is A cross B? A cross B is perpendicular to both A and B, the plane containing A and B. Okay, I'll give you an example. This is A, this is B. Where is A cross B? How do you find A cross B? Put a screw here at the junction, screw, right-handed screw, and turn the screw in the clockwise direction. In the whole world, wherever you go, if you turn a screw, the screw will go into the board, So if A is on the board, B is on the board, A cross B is into the board, B cross A is out of the board. Okay, so anyway, it is perpendicular to both A and B. A cross B is perpendicular to both A and B, or the plane containing A and B. Similar way, P cross A, torque is where? Perpendicular to both P and B. Where is P? Where is E? P is here, E is here. So where is P cross E? Into the board. So when you write, it should be into the paper, I'm repeating because you are writing on a paper, I'm writing on a board. That's the difference, okay? I'm repeating one more time. You learned in first year classes that A cross B's direction is perpendicular to both A and B. Okay, A cross B will be always perpendicular to A and B. Or A cross B will be perpendicular to the plane containing A and B. Okay, so if this is A, if this is B, I put a screw here. at the junction. I turn it in the clockwise direction. The screw is going into the board. So A cross B will be going into the board. Similar way, this is P. This is E. So where is P cross E? P cross E, you put the screw here, turn it from P to E. The screw is going into the board. So where is P cross E then? They are asking you to find the direction of torque. So you should write the answer this way. It's a repeated question. Torque is perpendicular to both P and E, or plane containing both P and E. Or you would say into the plane of the paper, notebook or exam sheet. Did you understand? So we have seen the equation for torque. Torque is given by P cross E. This is the equation for mathematical formulation for torque. Torque on a dipole. Now, if I expand this, I get PE sine theta. All right. Now my question is, when is the torque zero? Torque is zero under two conditions. When theta is equal to 0 or theta is equal to 180. Okay. You put them over here, tau is equal to 0. Right. Because PE sine 0 is 0. P is sine 180 is 0. Because sine 0 is 0, sine 180 is 0. So there are two cases under which torque is equal to 0. All right. Now before moving ahead, I'll tell you about one equation that belongs to next chapter. In your textbook, this equation is given in the next chapter. But I'm telling you now because there is a very important question that comes from this section. Okay. So I'll tell you the potential energy of a dipole is given by minus PE cos theta. This derivation will be done in the next chapter only. Minus PE cos theta, potential energy of a dipole. Because you learn potentials in the next chapter, then comes potential energy. Then there you learn potential energy due to dipole. Sometimes in schools, they might be taking this along with this section. But anyway, just know the equation. What is the equation for potential energy? Minus PE cos theta. Minus PE cos theta. Potential energy due to a dipole. Potential energy of a dipole is given by minus PE cos theta. Repeating one more time, we have written the equation for torque, and torque is given by P cross E, which can be expanded as PE sine theta. And then I'm talking about a condition here. Let us look at the condition here. I'm going to make torque equal to 0. Torque is equal to 0. This is my condition, right? I have two cases then. One is theta is equal to 0. Second one is theta is equal to 180. Both these would satisfy my equation, right? If you put theta equal to 0, you would get what? P is sine 0 is 0. If you put theta equal to 180, that would make it P is sine 180. Sine 180 is also 0. Now, what is this condition called? This is called equilibrium. Equilibrium. So, we are actually talking about equilibrium of the dipole, equilibrium. So, you say that a system is in equilibrium when the net torque is 0, net force is 0, or net torque is 0. Since it is rotational motion here, we are talking about torque. This is called rotational equilibrium. So, the point is what? The dipole is said to be in rotational equilibrium. The dipole is said to be in rotational equilibrium when torque is equal to 0. This can happen under two circumstances. One is theta equal to 0. Second one is theta is equal to 180. Now, let us see what happens to energy then. I'm going to put potential energy here. U is equal to minus PE cos 0. Look at this. I put theta equal to 0. That is minus PE into cos 0 is 1. That makes it minus PE. Minus PE means what? Potential energy is, this is called minimum energy. Minimum. Potential energy is minimum. And this condition is called stable equilibrium position. Equilibrium, stable equilibrium position. Why do we call it stable equilibrium position? Because energy is minimum. Nature loves what? Minimum energy. That is why things try to attain, objects try to attain stability, stable equilibrium. So, stable equilibrium happens when energy is minimum. What about the other case? You put theta equal to 180. You find the potential energy there. U is equal to minus P into cos 180. So, that makes it what? Minus P into cos 180 is minus 1. Minus or minus is plus PE, which means what? Energy is maximum. This is maximum. This was minus PE, that is minimum energy. And this is plus PE, which is maximum energy. Maximum energy means what? That is called unstable equilibrium. Unstable equilibrium. Okay. So, the question, the previous board question is, find the work done to rotate the dipole from stable equilibrium position to unstable equilibrium position. How do you find stable equilibrium position? Means you have to put theta equal to 0. Unstable means theta equal to 180. Theta equal to 180. The work done equation is, that will come in the next chapter, minus PE into cos theta 1 minus cos theta 2. That will be the equation for work done to rotate the dipole. I am repeating the whole thing one more time. Trust me, this is very, 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 very important. You must have already seen this in school examinations because it's so important. Okay, so what about the torque of a dipole? Torque on a dipole in a uniform electric field is given by torque is equal to P cross C. And upon expanding, it is what? Tau is equal to P E sine theta. All right. And then torque is to be 0. This is my condition. What is the condition here? This is called equilibrium. Rotational equilibrium. Even otherwise, we have seen this many times. You know, equilibrium happens when force is equal to 0 or torque is equal to 0. So, in this case, we are looking at rotational motion. So, rotational equilibrium is the case under consideration. Okay. So, rotational equilibrium happens when torque is equal to 0. Torque becomes equal to 0 when theta is either 0 or 180. Sine 0 is 0. Sine 180 is 0. So, that leaves me with two cases. Theta equal to 0, theta equal to 180. Then you think about the potential energy. I wrote down an equation for potential energy here. That actually belongs to next chapter. Minus PE cos theta. P is dipole moment, E is electric field, cos theta is the angle. Okay. So, minus PE cos 0. I put the first condition. Cos 0 is 1. So, minus PE into E. That is minus PE. Potential energy is minimum. Potential energy is minimum means it has maximum stability, right? Maximum stability. Stability is maximum when energy is minimum. So, this is called stable equilibrium. And theta equal to 180. When you go to the next case where theta is 180, U is minus P into cos 180. Cos 180. Cos 180 value is what? Minus 1. Minus or minus is plus PE. This is what? Plus PE is maximum energy. Maximum energy means unstable equilibrium. Minimum energy is stable equilibrium. Maximum energy is unstable equilibrium. The question will be like, what is the work done to rotate the dipole from stable equilibrium to unstable equilibrium or unstable equilibrium to stable equilibrium. How do you find? Work done equation is this. This derivation also comes in the next chapter. Work done is given by minus PE into cos theta 1 minus cos theta 2. What is theta 1? You know, just imagine they are asking you to find the work from stable to unstable. That means theta 1 is 0, theta 2 is 180. On the other hand, if they ask you to find the work done to rotate it from unstable to stable, theta is 180. So theta 1 should be 180, theta 2 should be 0. Did you understand? Calculate the amount. Previous board question. Calculate the amount of work done. 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 Calculate the amount of work done in rotating a dipole. Calculate the amount of work done. So you have to calculate the amount of work done. Calculate the amount of work done to rotate a dipole. To rotate a dipole of dipole moment. I have written here. Calculate the work done to rotate a dipole. Calculate the amount of work done to rotate a dipole of dipole moment 3 into 10 power minus 8. Of dipole moment 3 into 10 power minus 8 coulometer from stable equilibrium position to unstable equilibrium position. Stable equilibrium position to unstable equilibrium position. Stable equilibrium position to unstable equilibrium position in an electric field of strength. 10 power 4 Newton per Coulomb. 10 power 4 Newton per Coulomb. Electric field of strength 10 power 4 Newton per Coulomb. I can repeat the question. Calculate the amount of work done to rotate a dipole of dipole moment 3 into 10 power minus 8 coulometer. This is not centimeter, coulometer. From stable equilibrium position to unstable equilibrium position. Remember, stable to unstable. In a uniform electric field of strength 10 power 4 Newton per Coulomb. Did you get the question? Let us put the values. You know what is stable equilibrium means? Theta 1 is 0. You are going from where to where? Stable to unstable. Stable to unstable. Question paper says that you are moving from stable to unstable. It is not the other way around. Stable to unstable. Stable means what? Theta 1 equal to 0. Stable means theta is equal to 0. Unstable means theta is equal to 180. Unstable, right? Okay, so let us find the equation for work done. Let us do it together. Minus P into cos theta 1 minus cos theta 2, right? Minus P into cos theta 1 minus cos theta 2. Do you remember this equation? We wrote it earlier, no? This is work done to rotate a dipole from theta 1 to theta 2. So just put the values here. That is minus P into cos of theta 1 is how much? Theta 1 is 0, cos 0 minus cos of theta 2 is how much? 180 degree. So that is minus P into cos 0 is 1. Cos 0 is 1 minus cos 180 is minus 1. So tell me what? Minus P into 1 minus minus 1. 1 plus 1, 2. So minus 2 PE. Put the value minus 2 into P is there. 3 into 10 power minus 8 into electric field is there. 10 power 4. What do we get? Minus 2 into 3 is 6. 10 power minus 8, 10 power minus 4, 10 power minus 4 joules. Work done is measured in joules. Did you understand? This is a frequently asked question. Same question comes in magnetism and matter also. There, instead of PE, you'll be using MB. Magnetism and matter, same question is there. There you'll be using MB. The stable, unstable, everything will be there. Did you understand? See, I'm putting it on record. I made a mistake. This is, the equation is not minus P, it is plus P into cos theta 1 minus cos theta. It is minus, but it is the other way around. Cos theta 2 minus cos theta 1. Okay, it's my mistake. If you take it as minus, this will be cos theta 2 minus cos theta 1. But it is better to take it as plus. So it was a mistake from my side. PE into cos theta 1 minus cos theta 2. PE into cos 0 minus cos 180. So that makes it plus 2PE. So everything is plus 2. Did you understand? Next topic is electric flux. What is meant by electric flux? I'll tell you. You know, we have a surface here. This is a surface, no? And I've taken a small area over it. Small area over it. The area vector is drawn like this. Area vector. I'm drawing the area vector. The area vector is called ds. Why is it called ds? ds is a small amount of area. Small amount of area. Look at this. I've taken my palm. Look at my palm. This is the big area over which I've taken a small area here. I've drawn an area here. No, you can see this. This is small area. Okay. Now this is called area vector. Area vector is always perpendicular to the surface. And there is an electric field line going in this direction. Electric field line. Electric field line is penetrating it at an angle theta. I can resolve this vector into two. One component here and one component here. The component near to theta is E cos theta, and the component away from theta is E sin theta. I'll explain this. Look at this. This is the big surface is my palm, and this is a small surface. I've taken the area vector, and an electric field line is going in this direction. Look at this. Look at this. This is area vector, as you can see. Look at my palm. Look at my palm. Right. This is area vector, no? Right. And the field line is going in this direction. Okay. And then I split this field into two components. I can resolve any vector into two components. The component near to theta is E cos theta. The component away is E sin theta. Then what is flux? Flux is defined as the product of normal component E cos theta and area vector. So what is product? What is flux? This is a previous question. How do you define flux? We won't take tangential component. By definition, look at this. This is the area vector. This is field line. I can split this into two. One here, one here. Normal component, that is E cos theta, multiplied by area is called flux. So this looks like what? A, B cos theta. AB cos theta is A dot B. A dot B. So this is how small flux is written. D phi is equal to E dot ds. Actually, what is flux? I'll tell you. You know, this is a surface. A line is penetrating it. I split that into two. Another line is penetrating it. I split that into two as well. Another line is there. That is also split. Another line is there. That is also split. So all the lines are split and all the perpendicular components alone are added together. That is called flux. And that is mathematically done using this. Understood? That is the physical meaning of flux. What is flux then? If I have a surface, I have so many lines going in this direction. I split this into normal component, tangential, normal component, tangential, normal component, tangential, normal component, tangential. Then all the normal components are being added up. That is the meaning of the term flux. This is actually small flux because it is passing through the small area. So if I have the small flux, I can find the total flux by using the process of integration. That is integral E dot ds. That is the equation for flux. I'll quickly repeat this one more time. Look at this. We have a surface here. This is a big surface, no? And on the surface, I have taken a small area. This is area vector. Area vector is always perpendicular to the surface under consideration. And then what? This is the direction in which the field line is going. Look at this, field line is going. That field line can be resolved into two components. Component near to theta is E cos theta. Component away from theta is E sin theta. And then flux is defined as the product of normal component. That is definition. Don't ask me why. That is definition. E cos theta and ds. E cos theta and ds. This looks like what? A, B cos theta. A, B cos theta, which is A dot B. So E ds cos theta will be E dot ds. This is small flux through small area. If I want total flux through total area, it will be what? Integration. Okay, if you want to find the mass of Pacific Ocean, you take 1 cup of water from Pacific Ocean, then integrate it over the volume of Pacific Ocean. You will get the total mass. That's what the technique is all about. You find the small flux, you integrate it, you get the total flux. What is the physical meaning of flux? I told you there are, lines going like this, one here, one here, one here, one here, one here. There are many lines going, penetrating the surface, and all the lines are resolved into perpendicular, tangential, perpendicular, tangential, perpendicular, tangential. And all the perpendicular components are, these perpendicular components are being added up. And that is the meaning of the term flux. Did you understand, everyone? So we have seen what flux is. We are going to Gauss's theorem. What is Gauss's theorem? According to Gauss's theorem, this is a charge, okay? According to Gauss's theorem, the flux coming out of a Gaussian surface is equal to 1 by epsilon 0 times the charge enclosed by the surface. So what is a Gaussian surface in the first place? Gaussian surface is one who encloses the charge. That means the one which covers the charge. But anything can be a Gaussian surface. But the problem is, that will be complicated in some cases. So we'll stick to 3 types of Gaussian surfaces. One is spherical Gaussian surface, again cylindrical Gaussian surface, and cubical Gaussian surface. Did you hear me? I'm repeating. Gaussian surface is what? Gaussian, Gauss theorem. We are learning Gauss theorem where we have Gaussian surface first. Gaussian surface. What is Gaussian surface? Any closed surface which is imaginary. This is an imaginary surface, okay? Gaussian surface is an imaginary closed surface that encloses a charge. Repeat after me. Gaussian surface is an imaginary, such a surface does not exist. Okay, it's an imaginary surface, a closed surface. It should be enclosing a charge. And there can be 3 types of Gaussian surfaces. One is spherical Gaussian surface. Second one is cubical Gaussian surface. Third one is cylindrical Gaussian surface. Again, spherical Gaussian surface, I can simply draw a sphere around this. This is spherical Gaussian surface, okay? Number 2, cylindrical Gaussian surface, cylinder. Number 3, we'll have questions coming up later, okay? Number 3, cubical Gaussian surface, okay? And then look at this. This is my charge plus Q. And see this, lines are coming out of this, lines are coming out of this. Because from positive lines are going in all directions, no? So what is flux then? Flux can be calculated using 1 by epsilon 0 into Q enclosed. The flux is given by, flux coming out of a Gaussian surface is given by 1 by epsilon 0 times the charge enclosed by the surface. Did you understand? There are numericals on the paper. We'll come to the paper, but before that, I'll do some extra questions, okay? Let's just start writing. Question number 1. Calculate the flux linked with, question number 1, 1 Coulomb charge. Question number 2, dipole. Previous questions. Calculate the flux linked with 1 Coulomb charge. Yeah, 5 to 7 minutes. Vishal. Calculate the flux linked with. Question number 1, calculate the flux linked with. Calculate the flux linked with. Calculate the flux linked with 1 Coulomb charge. Calculate the flux linked with 1 Coulomb charge. Second one, dipole. Or they'll ask like calculate the number of lines linked with number of lines coming out of plus 1 Coulomb. Calculate the number of lines coming out of plus 1 Coulomb. Number of lines coming out of plus 1 Coulomb means what? Same as flux. Okay. Calculate. What is the question? Calculate the flux linked with 1 Coulomb. Number 2, dipole. So let us write the answers number 1 by 1. Okay. First one. Answer to first question. 1 Coulomb. So I take this 1 Coulomb and then what? I enclose that in a Gaussian surface. That's it. That's the end of it. Then I can calculate flux. Flux is what? 1 by epsilon 0 into charge enclosed. So 1 by epsilon 0 is 8.85 into 10 power minus 12. Epsilon 0 value you learn, no? Into 1. If you calculate it, 1.13 into 10 power 11. Newton per coulomb into meter square. That will be the unit. Okay, it's a standard question. That is why I remember the value. It's very important. Okay. The question goes like this. Calculate the flux linked with 1 coulomb charge, or calculate the number of lines of force coming out of 1 coulomb charge. Calculate the flux linked with 1 coulomb charge, or calculate the number of electric lines coming out of 1 coulomb charge. Look at this 1 coulomb charge. Lines are coming out, lines are coming out, lines are coming out. No, but all lines are perpendicular. So all are contributing to flux. All are contributing to flux. So if they ask you to find the number of lines, just find out flux. Flux is 1 by epsilon 0 into Q. That is 1 by epsilon 0 value is how much? 8.85 into 10 power minus 12. Into charge enclosed is 1 coulomb. You put it over here, and then that is, if you calculate, you're getting what? 1.13 into 10 power 11. Flux's unit is Newton per coulomb into meter square. Okay. That is question number 1. Question number 2, part 2. I have to take a dipole. So you enclose the dipole within a system, I mean Gaussian surface. Enclose it within a Gaussian surface. Apply Gauss theorem. Phi is equal to 1 by epsilon 0 into what is the charge enclosed? 1 by epsilon 0 into plus q plus minus q. Because there are 2 charges enclosed. It is what? Answer is 0. 1 by epsilon 0 into 0. That's correct. Common sense. Why? Because line starting from plus will end on minus. Line starting from plus will end on minus. Nothing will come out. So flux is 0. Repeating one more time. So first question is flux coming from 1 coulomb. That we have done. Second one, flux coming from a dipole. Dipole means 2 poles, plus q and minus q. I'm just enclosing that within a Gaussian surface. Then I apply Gauss's theorem. Gauss's theorem says what? Flux is equal to 1 by epsilon 0 into whatever is inside. One is plus q, the other is minus q. So plus q plus minus q. Plus q plus minus q is what? 0. 1 by epsilon 0 into 0, 0. So no flux is coming out. That makes sense, no? Plus q, lines are coming from plus q, they are ending on minus q. Did you understand? Okay, calculate, find the ratio of, find the ratio of fluxes through the spheres S1 and S2. Find the ratio of fluxes through the spheres. Find the ratio of fluxes through the spheres S1 and S2. Ratio of fluxes through the spheres S1 and S2. Did you get a question? Find the ratio of fluxes. Ratio of fluxes is to be calculated through S1 and S2. How do you find ratio of fluxes? Tell me. Flux through the first sphere, inner sphere. Flux through the first sphere. Inner sphere is a Gaussian surface, no? Inner sphere, S1. What is the flux through it? 1 by epsilon 0 into whatever is inside it, Q. Can this be counted? No. Why? It is outside. Only enclosed charges can be taken. Does the sphere enclose this Q? No. It is outside. Now what about flux through the second sphere? 1 by epsilon 0 into Q plus Q. Why did I take Q plus Q? Because when you look at the outer sphere, both the charges are enclosed, Q and Q. Am I correct? So that makes it 1 by epsilon 0 into 2Q. So if I take phi 1 by phi 2 ratio, which is a question, I get what? Q by epsilon 0, first one. Second one is 2Q by epsilon 0. Q and Q are cut, epsilon 0 cut. The answer is 1 by 2. Repeating one more time. There are 2 spheres here. These are concentric spheres. Concentric means what? Same center. They have same center here, no? I have placed one charge here inside the inner sphere. another charge in between the inner sphere and outer sphere. They have asked you to find the ratio of fluxes through the spheres. So if I consider the inner sphere, the flux is what? Flux 1 is equal to 1 by epsilon 0 into q. Why should I take this q only? Because this q is outside. Gauss's theorem says that only enclosed charges can be taken. Enclosed means inside charges. Inside this, I got q. Similar way, I take the outer sphere. Outer sphere, when I take, the outer sphere encloses what and what? This q is inside, this q is also inside. So I have to count both, q plus q, that is 2q, 1 by epsilon 0 into 2q. Then find the ratio phi1 to phi2, q by epsilon 0, this is 2q by epsilon 0. The ratio is q by epsilon 0 gets cancelled, you're getting 1 by 2. Did you understand this? I'll do that in the next class, but I'll tell you one question. You know, if I have a sphere here which has a charge q, flux coming out of it is phi. If I make it a bigger sphere of double the radius, even now the flux is same. Because if I take one sphere, smaller sphere, the lines coming out will remain the same even if I choose a bigger sphere. Same lines are passing through what? Same lines are passing through the outer sphere also. Understood? So just know that even if I increase the size of the Gaussian sphere, flux does not change. I have a small sphere inside which I have a charge q. If I make it a bigger one, the flux remains the same. Did you understand?